Low Voltage Breaker Course Section 11. Selection Criteria, Matching the breaker to the application. A step-by-step selection guide. Welcome to Section 11. We have identified all the major breaker types and decoded their labels. The final crucial skill is putting it all together, selecting the right breaker for the right job. This is a three-step systematic process. Step 1. Determine load current. The first step is sizing the breaker for the continuous load and the wire. You must calculate the maximum continuous load current that the circuit is expected to draw under normal, running conditions. Ampacity Rule. The breaker's rated current must be equal to or less than the ampacity, current carrying capacity, of the conductor it protects. This is essential, as the breaker's primary function here is to trip before the wire insulation degrades or overheats. Step 2. Determine fault current. The second and most critical safety step is finding the maximum available fault current at the point of installation. This value is determined by calculations involving the power source, transformer size, and the impedance of the cables leading up to the breaker. The crucial car match. The breaker's short-circuit breaking capacity must be greater than the calculated maximum available fault current. If the car rating is insufficient, the breaker is unsafe and could fail violently upon a short circuit. Step 3. Assess load characteristics and protection needs. The final step is to consider the nature of the electrical load and the required level of safety protection mandated by code. This determines the type and sensitivity of the device. Load type, curves B, C, D. If the load is highly inductive, like a motor with high starting surge, you will need a type D MCB. If it's a standard general-purpose outlet, a type C is appropriate. This is how you prevent nuisance tripping. Human protection requirements. Does the circuit feed a wet area, kitchen, bathroom, outside? If yes, local electrical codes will mandate human shock protection with an RCCB, RCD or GEFC. This adds a layer of safety separate from the overcurrent protection. Fire protection requirements. Does the circuit feed a sleeping area or a critical space? You may be required to install an AFCI AFDD to detect and interrupt dangerous series and parallel arc faults that standard breakers miss. Selective coordination. For large commercial or industrial systems using MCCBs, the selection process also involves setting the trip unit delays. You must ensure that the instantaneous trip of a downstream breaker is lower than the trip point of the upstream breaker to maintain selective coordination. Compliance and standards. Always ensure the final selected device, whether an MCB, MCCB, RCD, or AFCI, is certified to the relevant IEC or national standards, confirming its performance specifications are reliable. Up next, longevity and safety. We now know how to select the right breaker. In our final section, we will discuss the best practices for installation and maintenance, ensuring both your safety and the longevity of your electrical system.